Let's find the electric potential of a circular rod that's positively charged at a point along the axis of the rod. So recall that the change in potential is equal to 1 over 4 pi by the permittivity of free space by the differential charge on the radial distance from that differential charge to the point we're looking at. So if we take a differential charge somewhere along this rod, we have a radial distance from that differential charge to this point, and the radius of this circular rod is constant. And we'll also label the z distance to the point. So using the geometry of the circle, we have the differential charge is equal to the linear charge density multiplied by the differential arc length. So that would be r d theta. And using Pythagoras' theorem, r is equal to the square root of z squared plus r squared. So if we make those substitutions, we get 1 over 4 pi epsilon naught by lambda r d theta, and that's divided by root z squared plus r squared. And if we sum up the differential potentials due to those differential charges all around that rod, so effectively we integrate, that gives us the total potential at this point. So if we take constants outside the integral, we get lambda r on 4 pi epsilon naught, and square root z squared plus r squared can also be taken out of the integral because they do not depend on theta. So we're integrating over theta. Okay, so if we look at the plan view, this here is d theta, and we integrate from 0 to 2 pi around that circle. So effectively what we get is lambda by 2 pi r over 4 pi epsilon naught root z squared plus r squared. And we can make some cancellations of pi, and 2 on 4 is a half. So what we get is the electric potential is equal to lambda r on 2 by the permittivity of free space by the square root of z squared plus r squared.